Session is 1 hour, including the discussion.
Okay.
Okay.
Once again, a very warm good morning to one and all. It's my pleasure to welcome you all to the third day of SECON'22. This is our fifth Keynote lecture. Before we begin, I request all of you to please switch on your videos and mute your audio till the end of the section. Also, if you have any queries regarding the topic, please don't hesitate to put it in the chat box. Now I welcome Shriya Raj P to address the gathering and introduce our keynote speaker.
A warm welcome to everyone present here. With great honor, I would like to welcome the guest of the day, Dr. Pierce Changsali, who will be the speaker for today's keynote lecture. I also welcome the audience who has graced the event with their presence. With great pleasure, I would like to give a brief introduction on our speaker, Dr. Pierce Changsali. Dr. Piyush Changsali is an assistant professor in the Department of Civil Engineering at the Indian Institute of Technology, Madras, Chennai. He received his BTech in Civil Engineering from NIT Warangal, MS in Civil Engineering from Clarkson University, USA, and PhD in Civil Engineering from the University of Illinois at Urbana-Champaign. During his PhD at the University of Illinois, he was a recipient of Ravinder K. and Kavita Kimbra Fellowship and Chester P.C.'s Research Award. Before joining IIT, he was a postdoctoral associate in the Department of Material Science and Engineering at Massachusetts Institute of Technology, USA. He is an active member of American Concrete Institute, Indian Concrete Institute, and RILEM. He currently serves as an editorial board member of ASCE Journal of Materials in Civil Engineering. He is broadly interested in processing microstructure performance relationship of alternative cementitious binders and thermodynamic modeling of hydration of cementitious materials. Welcome, sir, to the session.
Thank you for the introduction. It's my pleasure to present my work. Let me start sharing, and thanks to all participants who are here. Yeah, I guess it should be now visible. Can you confirm,
sir.
please?
Yes.
Okay.
Yes, sir.
Okay. Okay. So the topic of my talk is calcium sulfur-aluminate belite cement, which have been promoted as a low CO2 binder. And I will give a context to this. Okay. So if we look at historical growth in cement and steel production, what we notice that in last 65 to 70 years, the growth in cement production has been significantly higher than the steel production. Okay, that's evident from this plot which I'm showing you. And you also see how fast population has grown. So there has been tremendous increase in the cement production globally. And if you look at the numbers, cement is used to make concrete, and roughly 30 billion tons of concrete is produced worldwide annually. So that's a very huge number. And cement manufacturing contributes to roughly 8% of global CO2 emissions. So there's a significant carbon footprint cement manufacturing has associated with. So there has been a push, to reduce carbon footprint of the cement manufacturing so that we can cut down the carbon footprint of concrete. And again, these charts show you comparison. So left one is, if you look at just a building and you see existing building versus new construction, and you see the contribution of construction and maintenance, right, towards the global CO2 emissions. So relatively, if you compare new construction versus existing buildings, existing building, the heating over lifetime contributes to larger chunk, right? Newer construction, basically this shear is less. But still you see how much shear construction and maintenance has. And now if you look at the construction, right, a building, one building for an example, significant fraction comes from concrete, right? There are other materials also like a steel, bricks, windows, insulation, but see the contribution of concrete. And now in concrete, we know we have cement, gravel, sand, etc., other SCMs. So significant again part of carbon footprint in concrete is because of the cement manufacturing. Okay. So, and we know that cement manufacturing, we use limestone, and the decarbonation of limestone, limestone. So this much contribution is from decarbonation of limestone or decomposition of limestone, where CaCO3 decomposes into calcium oxide and CO2, leading to CO2 emissions. So this is what happens, and we saw that the significant amount of concrete which is being produced annually at global scale, there is a need to look for alternative binders, right, which will have lower carbon footprint. So they will offer sustainability at the same time without compromising on other properties. So with that context, I'd like to introduce this cement, calcium sulfoaluminate belite cement. Some of you may have heard of it, many of you may not have, but we'll go through the basics. So basically, CSAB cement, calcium sulfoaluminate belite cement, contains these phases, which are C4A3S, which is calcium sulfoaluminate, C2S, C4AF. And we know that we are quite familiar with Portland cement, which contains C3S, C2S, C3A, C4AF, right? So what we notice that the CSAB phase does not have C3S. That's the main difference, okay? And also it doesn't contain C3A phase. And to make CSAB cement, we don't have to go to really high temperatures. So for an example, for Portland cement, we have to go to 1450 degrees Celsius, but the CSAB cement can be manufactured at 1250 degrees Celsius. So there is a reduction in the temperature requirement to manufacture this cement. And the raw materials are similar to what we use for Portland cement. So limestone, clay, bauxite, and gypsum. And if you look at the phase composition, yeelimite, the C4A3S is the calcium sulfoaluminate phase, is also called yeelimite. And because Alexander Klein patented this, so it's also called Klein's compound, C4A3S bar. Apart from yeelimite, this cement contains belite, C4AF, tetra calcium aluminoferrite, and calcium sulfate. And what you see in this bar chart is the CO2 per gram of phase. Let's say if we have to make 1 gram of C4AF or C4A3S, how much CO2 will be released? Just looking at the stoichiometry. So significant reduction can be seen, right, in case of C4A3S manufacturing. See the contribution of C3S, right? So overall, we can reduce the carbon footprint in CSAB cement manufacturing. And obviously this phase composition changes and that affects the properties. So that's what I will discuss, how different phase composition will give you different properties and how can we manipulate these properties. So overall, good news is there is a less carbon footprint of CSAB cement. Again, this ternary diagram shows comparison between PC, which is Portland cement, and CSAB. And what you see, CSAB cement has more alumina. So in this direction, the alumina content is increasing. In this direction, silicon content is increasing. In this direction, calcium content is increasing. So we can see generally CSAB phase composition, we are closer to this corner. So it has more alumina and less calcium. So less limestone is required to manufacture this cement. So that also results in reduced carbon footprint associated with the manufacturing of CSAB cement. So hydration of CSAB cement is different than what we see in Portland cement. So this C4A3S, which is calcium sulfoaluminate cement, can just hydrate in presence of water and form monosulfate. Monosulfate is the phase we also see in Portland cement hydration, when later on eternite converts to monosulfate when the gypsum depletes, right? Apart from monosulfate, you have formation of aluminum hydroxide. This is the reaction which takes place just in presence of water. But since we have gypsum in the system, again we are using the cement chemistry shorthand notations. So please refer to these for more clarity. So yeelimite phase can react with gypsum and form eternite. This is the eternite. AFT phase also gives you aluminum hydroxide. Now, if there is, let's say, if CSAB cement is mixed with Portland cement, or we supply additional calcium hydroxide, CH, now we have larger amount of eternite which is formed. So these two reactions contribute to expansion, and we'll see how we leverage that expansion to our advantage. Since I mentioned that CSAB cement may also contain belite, C2S hydration will lead to formation of CSH and calcium hydroxide, as we know. In this case, what happens, since AH3 is formed, C2S can also react with AS3, aluminum hydroxide, and form this another phase, C2ASH8, stratlingite. So you can see the phase composition, the hydrated phase composition of CSAB cement is different than Portland cement. This figure shows how these phases evolve with time. Starting, if we have CSAB cement where you have some yeelimite, so in this case what we see, this is the CSAB cement which had phase composition as this. So 54% yeelimite phase, 19% belite phase, anhydrite, and then some minor phases. And when we add water to it, what happens? So yeelimite hydrates, so you can see the reduction in the amount of yeelimite with time. All these phases are reacting, and what we are seeing the formation of phases like eternite, stratlingite, aluminum hydroxide, monosulfate. So these are the phases which we just discussed in the last slide. So these are the primary hydration products which are formed during the hydration of CSAB cement. And in this plot, you see that actually the thermodynamic modeling was able to predict how much of these phases will form, and this was verified using X-ray diffraction and TGA. So we know about the phase composition. Let's say now what happens to the hardening behavior, how quickly these CSAB cement harden, right? So that's also very important. So first let's look at this again, the ternary phase diagram. So you have basically belite is increasing in this, so this is the direction you can see. So depending on the amount of these phases, silicates, sulfates, ferrite, the hardening behavior of CSAB cement will be different. For an example, if the composition is somewhere here, you see rapid hardening, right? So if you have more sulfates, and also low durability in this case when we don't have much silicates, okay, or belite, let's say C2S is less, so that will affect the durability. And if we are away from sulfates, so the hardening is slow. So basically this gives you an idea. Depending on this, if you have a composition, you can get an idea about its hardening behavior, whether it will have a normal hardening behavior, whether it will be rapid or slow, and accordingly then we can manipulate, we can decide which admixtures to use. Let's say in this case, left side, this bar chart shows you citric acid was used to retard the hydration. So sometimes what happens, the hardening is very fast, and normal admixtures which we use in Portland cement do not work. So citric acid in this case has been shown to retard the hydration. So it gives us some time to work with this concrete, which contains CSAB cement. And here you see the effect of retarder, in this case citric acid, on two types of CSA1, CSA2. And you see that how the setting time was influenced by addition of citric acid. So citric acid has been shown to retard the hydration of CSAB cement. But more work, research is going on in looking at other admixtures also, which can be used to control the hardening behavior of CSAB cement. Yeah. So I said that when we talked about the hydration reactions, few hydration reactions, when you are forming atrenite in presence of gypsum, and when you have both gypsum and portlandite, you have formation of atrenite. Those are expansive reactions. So first of all, when we talk about expansion, suddenly we don't feel comfortable. But here what we are doing is we are using this expansion to chemically pre-stress the concrete. So I will explain what we see here. So if you look at the Portland cement concrete, for an example, you have a fresh concrete, right? And it's always under restraint. Either you'll have reinforced steel, it will have support, right? Or subgrade, it will be on something. So there is always going to be some restraint. And we know that with time, as it hardens, right, there is going to be shrinkage, drying shrinkage, as you call it. And that drying shrinkage, concrete is shrinking, but restraint is not letting it shrink. So what happens? Concrete is under tension. And we know that concrete is weak in tension. So what happens when the tension or tensile stresses exceed the tensile strength of concrete? There is a cracking. That's what happens. It's called restrained shrinkage cracking, right? We look at, you will take example of pavements, you see transverse cracking. A lot of times this is, so we would like to reduce the shrinkage normally, right? So there are some admixtures like shrinkage reducing admixtures people use to reduce this shrinkage, because if we are able to reduce this drying shrinkage, we will be able to control this cracking associated with it. But in CSAB cement, what happens? Because of those reactions which we just mentioned, there is an expansion of concrete. So there is a net volume increase. Now, if something is trying to increase its volume, and again there is a restraint will not let it expand, so there is going to be some compression. That's why we are calling it chemically pre-stressing. We are adding some chemicals, some chemical reactions are happening leading to expansion, and then expansion under restraint is going to induce compression in concrete. That compression now can take care of tension. So idea is, again, it's not like this concrete is not going to shrink overall, but the compression is going to take care of this tension. So overall, there is going to be the net, we can compensate for shrinkage through this expansion. So it's like C, which is compression, will take care of part of the tension or tensile stresses due to shrinkage. So CSAB cement can also be used for shrinkage compensation. So basically, 1960s, I mentioned that yeelimite is also called clay compound. So that time, a lot of work was done with the goal of achieving shrinkage compensation. Okay, so controlling this expansion and using this expansion to basically compensate for shrinkage. So we can also look at the dimensional changes. What you see in this case, during this hydration of yeelimite, there is a expansion. So we saw that earlier is the expansion. So you see there is change in the dimension. So this much expansion is there in expensive concrete. But this concrete also later on dries. So what you see, black curve is typically what you see for Portland cement concrete. So we say that this much of shrinkage is there, right? It could be 400 micron microstrain, 500 microstrain, 600 microstrain, depending on your type of concrete, what you have, and also environment. But by inducing this expansion, what we did, the net expansion is close to, I mean, we are able to compensate. You can manipulate this expansion so that where you can either have net expansion, or you can just compensate. You have close to zero shrinkage. So there is a reduction in the net shrinkage. That's what we mean by shrinkage compensation. So that's very advantageous when we want to develop a concrete which will prevent the shrinkage crack. Okay. Now we can have both expensive and non-expensive cements. In some cases, we don't want expansion. How do we then tailor or manipulate this property? So here you see M value is nothing but a ratio between gypsum and yeelimite. Yeelimite again is C4A3S, calcium sulfoaluminate phase. So this ratio will affect its hardening behavior and also expansion. So in this case, if the M value is greater than 1.5, what you see, the system expands. Okay, and if the M value is below 1.5, then it's not expensive system, but you are able to get rapid hardening, high strength. So as a user, this is one way to manipulate its expansion and accordingly the hardening behavior. So CSAB cement offers you both. It is a low CO2 binder because less limestone is used to manufacture CSAB cement. CSAB cement manufacturing requires rotary kiln temperature of around 1250 degrees Celsius. So you have 200 degrees Celsius difference. Also, this CSAB cement clinker is more porous than Portland cement clinker. So the grinding energy requirement, right, to make this cement is less than what is the requirement for Portland cement clinker. So there are so many advantages. That's why we said low CO2 cement, and we have seen that we can also leverage this expansion, which can be achieved for making shrinkage resistant cement. So both low CO2 cement, so sustainability and durability, right? Both can be addressed through the use of CSAB cement. So there are already standards. So I am showing you, this is the recent standard, shrinkage compensating concrete guide by American Concrete Institute, ACI 21, which goes through the design. Okay, how do we use these cements to develop shrinkage compensating concrete? So there is already this ACI standard, and in this standard they talk about different expensive cements. So one of them is type K, which is nothing but a blend of Portland cement and yeelimite, right, which is the calcium sulfoaluminate phase and calcium sulfate. So when we mix Portland cement with yeelimite and calcium sulfate, you get this type K cement. Okay, there are some other classes. Idea here again is all these are expansive cements, means there is an increase in volume as cement hydrates, and we use that expansion to basically design shrinkage compensating concrete. And towards the end of my lecture, we'll also see how do we use these guidelines to develop something like that, where we can compensate shrinking. Okay, but type K cement is basically a mix of Portland cement and CSAB cement. Some of the pictures, here you see a house that is all type K concrete. All roofs are monolithic concrete without roofing. The entire structure has only one joint. So here in the middle you have a Rockford Airport, 1200 feet post-tension taxiway without joints. So the spacing can also be reduced significantly. Here you have Toyota warehouse in Ontario, and for all these applications, type K cement was used. Okay. Those of you who are interested in knowing which are the companies which make CSAB cement globally, I have just listed a few from USA, Europe, and China. Okay, so there are already companies which make this cement. In some cases, they sell product like a concrete, right? In this case, you see here a zero shrinkage concrete product. Okay, rather than selling a cement, they will sell this concrete product. Idea again is to have expansion and use that expansion to develop something which can compensate the shrinkage. Okay, so this I'm just showing you various properties of CSAB cement and concrete. So left figure is for concrete. So in this case, what happened when CSAB cement can be used also as an expensive admixture, right? So as we saw that type K cement, basically type K cement is an expensive cement where CSAB admixture is used, right? So in that case, you see here basically CSAB cement enhances your strength, right? So Portland cement, when we add CSAB cement here, right, there's some increase in the strength, and obviously you see the effect of other admixtures in this case. So you don't compromise strength, right? When we use CSAB as an expensive admixture, in some cases you see increase also. So here is example of concrete. Here is example of paste. This is from our lab here at IIT Madras when CSAB cement is used in again expensive admixtures. In a paste, you see the strength increases, right? And 5 to 10%. So that's the typical replacement level, which is suggested around 10 to 15%. Because in this case, when we are using CSAB cement as an admixture, expensive admixture, we are basically inducing expansion. So this is basically OPC CSA blend, where 85 to 90% is OPC and 10%, 10 to 15% is CSAB. Again, this is for getting the expansion so that we can develop shrinkage compensating property. But we'll see later, in this case, CSAB cement is a sole binder. So you can have a CSAB cement which will not expand. Basically, it's a non-expensive CSAB cement, right? And we know that this will depend on M value. What is the M value? How much gypsum you have? What is the gypsum to yeelimite ratio? So we have both types, expensive, non-expensive. In this case, what is the advantage of this here is, one of the advantages of this cement is you are able to get very high early age strength. So in 6 hours, this CSAB cement is able to attain 20 to 25 MPa strength. Okay, this is again mortar strength, and with time how it evolves, you can see here. So this is just CSAB cement mortar, right? And what you see here, what is the effect of gypsum addition? Let's say if we add 5% gypsum, right? Because this non-expensive cement can also be converted to expensive cement. It all depends on M value, as we discussed earlier. If we increase the gypsum, to C4A3S ratio, that will lead to expansion. So we wanted to understand, let's say if we are getting expansion, does it compromise or does it affect the strength? So you can see this some influence on early age, but overall 7-day strength more or less same, right? So up to 15% of gypsum addition we looked at. Then also we looked at the effect of calcium hydroxide addition on top of gypsum. If we add some calcium hydroxide, how the strength evolves. So in this case, again, CSAB cement is a sole binder, means no Portland cement was used in this case. So what we see here, I will first focus on the expansion. So this is Portland cement, right? If Portland cement is kept in saturated environment, you see small, some swelling. So let's say 50 to 100 microstrain of expansion. But as we increase or the amount of CSAB cement in this case, so we are looking at the effect of CSAB doses, right? 5% addition led to increase in the expansion, and 10% you see significant increase. So by 10% addition of CSAB cement led to basically 3000 to 4000 microstrain, that much expansion. So an order magnitude higher just by adding 10% CSAB cement. But we have also seen that it doesn't affect the strength. So we are maintaining our compressive strength, but we are making this cement expansive, which can be used to make shrinkage compensating. And the curing environment also affects. So we have seen in this case, if we have saturated lime curing versus undersaturated case, undersaturated calcium sulfate. Let's say if we have undersaturated gypsum solution versus saturated gypsum solution. So how that affects? So we see that saturated gypsum case led to increased expansion. So when the gypsum is in saturated, when there is a supersaturation, right? So that what we are saying that exposure solution also affects the expansion. So non-expensive cement can be converted to expensive cement. So this is non-expensive, means the expansion is not significant, right? Non-expensive CSAB cement, through the addition of gypsum, what you see when we start adding gypsum, 5%, 10%, 15%, significant increase in the expansion can be achieved. So this is example of paste here. Now this 15% gypsum, if already have, further increase in expansion can be observed when we add calcium hydroxide. So in this study, what we showed is a non-expensive cement binder can also be converted to expensive binder. And we will see what are the differences, what basically happens. We know that when we have more gypsum, we'll tend to form more eternite. And also we know that when we have calcium hydroxide in the system, greater amount of eternite is formed. But we'll also look at, are there any changes in the pore structure, right? When we have so much expansion, can we differentiate non-expensive and expensive system based on the pore structure? So before that, CSAB cement, there is a reduction in the pH. So we know that Portland cement pore solution will have 13 to 14 pH, but as we in this case add CSA, there is a reduction in the pH. But in this study, we saw that still the minimum pH was around 13. Why it is important? Because when we talk about carbonation, right? When the pH is low, becomes 10, 11, then propensity towards carbonation increases, and carbonation then may induce corrosion. So a lot of work is going in that direction where people are looking at the carbonation of CSAB cements and what is the propensity of steel corrosion in these systems and how do we reduce that. So hydrate morphology, X-ray diffraction can be used to look at the phases which are formed during the hydration of CSAB cement, and you see here significant amount of eternite, right, which is the crystalline phase and responsible for expansion, right? As we increase the amount of gypsum, we see increase in the amount of eternite. Also, notice this is the Y is yeelamite peak, around 23.4 or 5 degrees 2 theta. We can monitor this, how quickly this is disappearing. Basically, this is a phase which is hydrating, right? By monitoring its amount with time, we can also estimate degree of hydration. Right side, again, this is developed using GEMS, which is thermodynamic, which can be used for thermodynamic modeling of these systems, and we saw the effect of calcium sulfate addition, right? And this is the modeling which is predicting, okay, with as you increase the amount of calcium sulfates, what will happen? The amount of monosulfate will decrease, amount of eternite will increase. Okay, that's what we also saw, and here modeling also predicts, and beyond certain percentage, you will be left with gypsum. And in addition to these phases, you have also aluminum hydroxide. So thermodynamic modeling also can predict which phases, what will be the stable phase assemblage, and that can be verified through experiments such as X-ray diffraction and TGA, because aluminum hydroxide which is formed in this case is not crystalline, so X-ray diffraction cannot detect this aluminum hydroxide. This can be identified using TGA. So a couple of slides back, I told you that non-expensive binder can also be converted to expensive binder. So what kind of changes happened in the pore structure? So what we saw, this is MIP results, mercury intrusion porosimetry, and we looked at the pore structure. So what we noticed is a clear difference between non-expensive system and expensive system. Okay, so this is the CSAB cement by itself, which doesn't expand, but upon adding extra sulfates in form of gypsum and calcium hydroxide, you see the shift in the peak. So critical pore size reduced in expensive systems, expensive cementitious systems. So we saw that as early as 1 day, and also we can see at 7 days. So this was the differentiating factor between non-expensive binders and expensive binders. So what is causing this? What is causing this shift in critical pore size? So we'll see that this expansion basically is influenced by M value, which is gypsum to yeelimite ratio, molar ratio, amount of eternite. More eternite you form, higher expansion will there be. Supersaturation with respect to eternite. What is the environment? What is the supersaturation? And also matrix stiffness, whether the stiffness is high or low, because basically these are the crystals which are in a matrix. If the matrix is not very stiff or not resisting this expansion, then we'll see the overall high expansion. So all these factors affect the expansion. So what is the mechanism, right? So Tabor did this experiment in 1916. So what he did is a saturated, there is a salt crystal, it's a saturated solution, and there is a weight. So there is a weight which is pressing this salt. Okay, this is the situation. So here is a saturated solution, not undersaturated, not supersaturated. Okay, saturated solution. So what happened when he allowed evaporation? So what happened? This solution became supersaturated, means concentration of ions increased, right? Part of, because water must have evaporated. So this solution became supersaturated. That led to increase, or that led to crystallization of the salt. So you see there's a crystallization, and that pushed this weight up. So this induced crystallization stress. So what is the driving factor for crystallization stress? It's the supersaturation. So supersaturation gives rise to crystallization stress. That's why it's important, if we can somehow estimate the supersaturation, we will get an idea about what degree of crystallization stress is there in the cementitious systems. So this supersaturation affects the pores, size of pores where crystals can precipitate. So in this case, eternite, because we know that the yeelimite hydration in presence of gypsum is forming eternite. So, and this is crystal. So point is, what you see here, two images. One is case of low supersaturation, one is case of high supersaturation. And this is the relationship between the curvature where the crystals can grow versus saturation index, or this is a measure of supersaturation. The point is, if you have high supersaturation, if the degree of supersaturation is high, that means the crystal can grow in smaller pores, right? So for high supersaturation case, you can see there are small pores which are not filled in this low case, but here they are filled, means crystals can precipitate in these smaller pores. Whereas if the saturation degree or supersaturation is low, crystals cannot grow. Okay, so filled pores means the supersaturated pores where crystals can grow. So that's how this supersaturation affects the precipitation. And by estimating this supersaturation, we can also calculate what will be the crystallization stress. Okay, this crystallization stress, and we can compare in situations. For example, I told you earlier, supersaturated when we are talking about the exposure solution. So when we had a saturated solution of gypsum, that led to the increase in expansion compared to undersaturated solution of gypsum. This is primarily because supersaturated solution of gypsum had higher saturation index. Okay, so we know that now this is the mechanism. So supersaturation is driving crystallization, and then these crystals are precipitating in the pores. When they precipitate in smaller pores, it induces higher stresses, crystallization stresses. Okay, so this is some of the recent work from our lab here at IIT Madras. We are looking at also the durability. So because of the high alumina content of CSCB cement, they are a potential candidate for applications such as sewage pipes, right, where the concrete is exposed to acidic environment. So we are looking at acid resistance of CSCB cement concrete, and citric acid being the most deteriorating acid. We looked at that, and you can see. So here you see this is the Portland cement, and also when 10% of Portland cement was replaced with CSA admixture, which is expensive in this case, and this is CSA cement, which was used as a sole binder, right? So we have two cases. So here this is expensive cement, this is non-expensive cement. So because of domination of PC, these PC dominated binders perished in just 2 weeks. Basically, you put these specimens in citric acid, and basically the binders perished. Compared to this sole binder, CSA cement, basically high eulemite cement, which was not perished. Obviously, with time it also deteriorated, but see the difference. So there's at least higher resistance of CSAB cement, in this case high eulemite cement, in citric acid exposure. You can see the difference, right? So here this is PC dominated, like Portland cement dominated, like Portland cement when it is 100% or when 10% is replaced with expensive admixture. So that's what happened. And here you see the high eulemite system. So current work is looking at different types of acids and different concentrations, so that we have a better idea which are like what kind of formulation will have higher or lower resistance. We are trying to understand this better. So this is final section where we'll look at how do we design CSCB cement concrete, right? So we have a cement. Now let's say if you want to prevent the shrinkage cracking, how do we use this cement to design that? So there are some design charts. So what happens, based on the location, we know that this much of shrinkage compensation is needed, right? Because shrinkage is driven by environmental conditions, like what are the conditions, like temperature, relative humidity, etc. So let's say we want to compensate this much level of shrinkage, okay? And here you have charts where you have percentage reinforcement starting from 0% to 2%. So what we do, depending on our percentage reinforcement, right, which is in the slab, let's say you are looking at a slab or bridge deck which has 0.3% in this case reinforcement. So what we see, we can then get, so this is on x-axis, you have a restrained concrete prism expansion. So as per the ASTM C878, we can cast these concrete prisms which are in the restrained condition, and we would like the expansion to be this much. So that will basically that will mean that if we now use that concrete in this case, in the slab which has 0.3% percentage reinforcement, will give you this much of compensation. Basically this much expansion will happen, and that will make this concrete shrinkage compensating. So this, what is this 878? So this is a simple test. You have a reinforcing bar and you pour the concrete, and then it is in restrained condition, and you measure the expansion. So this expansion, through this expansion basically we can design. So depending on, so if in this case the expansion is 0.05, right, roughly, let's say here. So these design charts can be used. Okay, we can derive, okay, for this much of expansion in the field, or this much of compensation we want, depending on the reinforcement, this much of restrained concrete prism expansion, and then design the mix so that we get this much of expansion here, 7-day expansion. So that's how we kind of design this shrinkage compensating concrete. Okay. So this is small scale versus large scale. When you do test, this is concrete prism. You have a Portland cement concrete which shrinks, and you see here 600 to 700 microstrain of shrinkage, right? Drying shrinkage basically. And in expensive concrete, you have early age expansion, but the net shrinkage is, in this case, very small, zero, close to zero. So we are using, so this concrete also shrinks, but the net shrinkage is reduced. That's the takeaway. And here you see example of a slab, right? Real slab, concrete deck, and we can see the difference in the two types of concretes. This much reduction in shrinkage. So I will show you field application. So this I was involved in this. So this is the bridge deck in state of Illinois in USA, where we developed this CSAB concrete, and then this was a test study where we wanted to see the difference between CSAB cement concrete and Portland cement concrete as far as shrinkage compensation is concerned. So we cast two slabs, one with the CSAB concrete. You can see it was quite workable, had good finish, and then we also cast the OPC, Portland cement concrete deck, next to this Portland CSAB concrete deck, right? So this is the final image, and we then looked at the cracking pattern, right? So you see here there were cracks in Portland cement concrete deck. Again, this is because of the shrinkage. So concrete tries to shrink because of the restraint. There is a tension, and that tensile stresses, when exceed tensile strength, will crack, concrete crack. So that happened in Portland cement deck, but these cracks didn't appear in CSAB concrete, right? So this was the example, I mean, the performance comparison between CSAB and Portland cement concrete. So as far as shrinkage compensation, resistance against shrinkage cracking is concerned, this cement is a solution for that. So let me summarize what we discussed and where we are, and where current efforts are being undertaken, right? So CSAB cement can offer up to 30% reduction in the CO2 footprint. So if you want to develop sustainable binders, so this is a potential candidate. Grinding energy requirement is lower, so because of the porous nature of CSAB clinker, you can attain rapid setting strength development using CSAB cement, and it has advantages. Let's say if you are want to open the traffic early, right? Because we don't want to hold things for a long time. So these situations, again, CSAB cement can be used. And this expensive characteristics, because the volume increase, can offer excellent resistance against shrinkage cracking. And we know that, once the concrete cracks, what happens? We are exposing our steel to atmospheric CO2 or chlorides, and then corrosion starts. And when corrosion starts, that basically will lead to degradation, right? So we want to prevent the cracks at first place. That's the idea. And in this case, expensive nature of CSV cement can be used to basically prevent shrinkage cracking. Current challenges, because of the use of bauxite, as I said, high alumina content, there is a high cost associated with it. So our lab here at IIT Madras is looking at basically alternative sources like the currently available waste materials which can be used to manufacture this. Reactivity of belite, because belite content can vary and also be in significant amount in these cements, and we know that belite C2S phase is not very reactive. How do we enhance the reactivity? Okay, that's current challenge. Chemical admixtures for controlling setting of rapid setting CSV cement, that is also currently being researched. And long-term durability against carbonation and steel corrosion, because the pH of these system is lower than Portland cement system, so there is a greater propensity to carbonate, and then when it carbonates, there is also propensity to corrosion. So there has been some work currently going on to look at that aspect. Okay. For you, those of you who would like to know more about this, we have written this paper. It's available through Indian Concrete Journal. CSAV Cements, Opportunities and Challenges. So it will summarize where we are and what are the way forwards, what are the challenges. So for more details, I would refer you to look at this. If you don't have access, feel free to email me. I'll be happy to send you. So finally, acknowledgements, part of the research which I showed here was supported by ICT at University of Illinois, and also current work is directed to understand the system better so that we can manufacture the cement in India, as there is no manufacturer currently making CSV cement, although there are some advantages. So acknowledge the support of IIT Madras and our AIMS lab here. With that, thank you for your attention. I'll be happy to take any questions you may have.
Thank you, sir. Now, if anyone have any doubts or clarification regarding the topic, please raise your hands or you can put it up in the chat box. So there is one question in the chat box. Can I read that for you?
Yes, let me just check.
Yeah, okay, sir.
Yeah, it's good question. So it's about predicting the rate magnitude of expansion while using non-expensive cement. So one simple way to control the magnitude of expansion is through addition of gypsum or calcium sulfate. Rate is difficult to control, but usually we have seen that whatever expansion occurs in first few days. So we want to ensure that the yeelimite hydrates completely in first few days. So within first week. I guess I didn't mention that it's very important to cure this cement for first 7 days, because if there is unhydrated yeelimite, later on it may hydrate, will lead to some local expansion and cracking. So early hydration of yeelimite is very important. For that, we have to ensure that the curing plays a big role. We have to insist on 7-day curing, not just 1-day curing. Okay, so these are some of the ways we can control the rate and magnitude of expansion. Yeah, how to proportion the concrete when we use this type of cement. So there are ways. It depends what type of concrete you want to make. If you want to make a shrinkage compensating concrete, let's say you are looking for applications such as pavements or bridge decks, slabs, then you follow the guideline. As I said, you have this test setup in the lab, ASTM 878, where we look at the restrained shrinkage. So, and when you get the desired level of expansion, and in the field, then we can look at what kind of compensation will there be. So as far as proportioning is concerned, the CSAB cement for shrinkage compensating applications, we replace 10 to 15%. of OPC is replaced with this expensive admixture. No, there is no Indian standard classification. We are working, first we have to show that it can be done in the lab. I'm hoping that it takes always time. We are doing the research and hopefully in future we'll see that happening. Yeah, so supersaturation is very important. It's like you take a glass of water, you keep adding salt, right? Initially you don't see salt because it's undersaturated. Now it will, as you increase adding salt, what will happen? At some point of time it will start precipitating, right? So you see here what is happening. The system is going from undersaturated system to supersaturated system. There are ways to calculate this supersaturation. You have to look at the concentration of ionic species and look at, let's say, eternite, what are the ions which are responsible, and then there are ways. I can send you papers for more details. Yeah, so adding gypsum to CSAB cement can lead to small reduction, but this is not very significant. When we use moderate levels of gypsum, let's say 10%, 15%, in 1 week, like 7 days strength was more or less similar. Okay. Yeah, very good question. Yeah, it's very important. So when we mine the materials, that involves energy. So we have to always look at the materials which are available, which are less energy intensive. So our focus here is to use materials such as red mud, for an example, right? Fly ash or other types of materials to basically manufacture this cement. You're right. So you will see that our group here, we are also looking at use of low grade limestone. So most of the significant amount of limestone is not cement grain limestone. There's a lot of limestone which doesn't, is not used to make cement because of, let's say, high siliceous content, etc. So we are looking at all these alternatives so that we can use these materials which are available and reduce the CO2 footprint and energy requirement to make this kind of cements. Yeah, there's no IS code available. Gypsum. Okay, gypsum will reduce the setting time. Will it affect the performance? We have seen that gypsum, obviously there will be some effect on the hydration part, but as far as strength is concerned, 10 to 15% gypsum doesn't affect the strength, but it will lead to expansion. So let's say it will make your system expensive, so that can be used for shrinkage compensation. So we would like to add gypsum only when we want some expansion. Okay. I think I have answered most of the questions which I saw here. Yeah. Yeah. So Indian conditions are different. You're right. We are hoping that at some point of time we'll have cement companies also making this cement. See, we are not saying that we want to replace OPC. This is type of cement which has some advantages depending on the application. So it's like no one size fits all, right? I always believe in that. So you have different options, and depending on, let's say, if you want to design concrete which has superior acid resistance, right? So you not necessarily need to go for Portland cement system. You have other alternatives. Similarly, if you want to design concrete for mitigating shrinkage cracking, then again you have some alternatives. So that's the idea. Our group here looking at different aspects like durability. So, and we, as I think one of the audience, one of the questions is related to aggressive Indian weather conditions. We are looking at carbonation, we are looking at acid resistance, we are looking at sulfate attack, etc. So again, just to keep that in mind. So hopefully in future we'll see more people working in India, and there will be push to make this cement. Although, I mean, because there are advantages and there are already people who are making this, so why not here?
Thank you, sir, for clarifying the doubts. I hope there is no other doubts. So there is a link to the feedback form is available in the chat box. Participants, make sure that you go through it so that you can receive your certificates. Now I call upon Ashika Martin to deliver the vote of thanks.
It was indeed a great privilege to have Dr. Piyush Chaunsali, Assistant Professor in the Department of Civil Engineering at the Indian Institute of Technology, Madras. I would like to thank him for enlightening us with his knowledge. His insightful lecture was of wisdom, information, and it was interesting indeed. It gave us deep insight into the topic and also revealed some interesting facts. Today, we had the opportunity to hear your thoughts, and this is definitely encouraging us in our future ventures. Once again, and thank you, sir, for having spared your precious time for all of us. Thank you so much, sir. With deep sense of appreciation, I thank our head of department, Dr. Gigi Anthony, and all the teachers for their untiring efforts. Also, I thank each and every one of you present here today for your attentiveness and kind cooperation. Thank you all.
Thank you to the
Yeah.
organizers. It's a pleasure. I'm happy, and thanks to audience, for asking questions. And anytime, any questions, feel free to email me. I'll be happy to discuss further. So you have my email. I'll be happy to share this presentation also if required. Thank you.
Thank you, Piyush, sir. Thanks once again.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.